types of photodetectors, which I'd like to discuss. The first one is a photomultiplier tube. This is quite well-known device. Actually, it was invented in Russia in 1930s by the Russian physicist Tversky. And now, despite that this device was developed almost 100 years ago, it remains useful and remains a conventional photodetector which is used in scintillators. And this device is pretty simple, and there are two mechanisms which allows you to detect light. And the main goal of this device, is to convert your photon into electric signal. That's the first purpose of this photomultiplier tube, and the second one is to amplify your signal. And how it works: you have a tube. It's vacuum sealed. There is vacuum inside, and you have a photon, which this is a light photon, which was created in a scintillation detector. You have, of course, a lot of them, but let's move to the simplest way: just one photon. And you have a glass window. Remember, I told you that you have a refraction index which is close to glass because you have glass window in the photomultiplier tube. And the second structure, which is located inside this vacuum tube, this is a photocathode. And photocathode, that's quite a thin structure, which allows you, due to the effect which I covered in my first lecture, which is called photo effect, to create an electron instead of photon. And how it happens: you have this structure. This is optical window, this glass window, and you have about 30 nanometers thick photocathode. That's very thick for a very thin material, because if you do it to make it too thick, it would be impossible for an electron to escape from the photocathode and go into this room, into this space. And what happens? That's simple photoelectric process, which I think you know. Photon is converted into electron, and this electron starts moving inside this vacuum tube. But in order to make it moving, you have to apply an electric field. To do this, we have this structure of these metallic pretty thin plates, which are located inside this vacuum tube, which are called diodes. They are made of metal as well. And the main thing of this, the main goal of these diodes is to amplify the signal and create more and more electrons. Here is the first process, photoelectric effect or photoemission, and the secondary process is called secondary electron emission. And what happens here? Electron is moving inside this vacuum tube and hits the diode. And as a result of this interaction, this electron gives rise to more electrons. There are more electrons emitted from from this Dynat structure. For example, for one electron, initial electron, you will have two electrons, and these electrons also interact with this Dynat, strike it, and create more and more electrons. And actually, you have some sort of an avalanche compared to the thing I mentioned about gas field detectors, but that's a little bit different because you have a vacuum here, and all electrons are produced through the interaction with this Dynat structure. And this process allows you to significantly increase the number of electrons. For example, one initial electron, at the end of this way, you will get up to 1 million electrons. So when these electrons comes to the last Dynat or the anode, you can collect them and get the electric charge. And this charge can be processed like in ionization chamber. You have a capacitor, a resistor, they will get an amplitude in voltages, and the amplitude, the value of this amplitude is pretty high compared to some other types of detectors, and you can use, for example, a simple preamp and feed it to your data processing system. The main disadvantage of this photomultiplier tube that in order to create this amplification, you have to apply pretty high electric fields up to 1.5 kilowatts of voltage in order to create about 100 volts of electron volts between all diodes, because if you get less, you will not get enough energy to create these additional electrons. And one of the most important parameters of the photomultiplier tube is called the quantum efficiency, because not all initial photons go to electrons, because there is also a probability. And on average, this number is from 20 to 30% quantum efficiency. Here you can see how this device looks like. Different geometries, different sizes. You have small devices with a diameter of about half of inch, about 1 centimeter, and two large EMTs with diameters for about 20 inches, half of meter. It depends on the size of the detector or the application of the device. Here that this delta number tells you the number of secondary electrons emitted per primary incident electron, and if you multiply the number of these Dynats and the probability to create the secondary electron, you will actually get their amplification factor, which is called a gain. And this number, as I said, can be up to 1 million, even more. But basically, it's something 5 times 10 to the power of 6. That's the gain. PMT quantum efficiency strongly depends on the light, because if you have the wavelength, the photoeffect process differs for different wavelength of a photon. For example, for ultraviolet photons, you have more energetic. Yeah, if the wavelength is shorter, you have more energy for your photon. That is why this quantum efficiency depends on the wavelength of your photon. And operating voltage, as I said, usually from 1000 volts to 2000 volts. Sometimes it's not important, but there are some also parameters, but I'm not going too deep into details. Should be time resolution, how quickly you collect your light, how transit time, how quickly electron avalanche moves inside this vacuum tube, linearity, because you have a uniform response to low flashes of light and to big flashes of light. You have to understand that your response is linear in a big energy region. And there are some spurious effect like dark noise, which is mostly caused by fermionic emission of electrons from the photocathode. And now that was a vacuum device which was invented almost 100 years ago. And during the development of semiconductor materials, physicists started to consider new opportunities to detect light and came up with an idea to use silicon, which is used in basic materials, semiconductors, transistor diodes, and so on. And they came proposed to use these silicon diodes in order to detect light. And the main difference here that you have not so-called external photo effect, which actually happens in this photomultiplier tubes, because your electron from the surface of the photocathode goes to the vacuum. Here is called internal photo effect. Then you your photon actually can create an electron inside these semiconductor materials. And this electron can, if you have a flash of light, this light gives rise to electrons. If you have pretty intense flash of light, you have a lot of electrons, and it leads to electric current in simple terms. And this is a device called a photodiode. That's some sort of semiconductor replacement to the photomultiplier tube, but it can't fully replace it for several reasons. And the first reason that in this semiconductor material you can't detect people lights, single photons. The main reason you don't have an amplification of this structure. You have the same thing. You have to apply it in electric fields, of course, in order to collect your electric charge. Yes, and this field is not high enough to amplify the signal, and you don't have gain. And if you don't have gain, you can't detect single photons. And physicists started to develop devices which can do this thing, and they proposed to apply high electric field to the photodiode and invented the second type of the photodiode, which is called avalanche photodiode, because they applied high electric fields to this semiconductor structure. And here you can see the picture. You have an initial photon which creates electrons, and these electrons start moving under the influence of electric field. And if you apply high electric field, like in gas detectors, you can create an avalanche. Raw electron has enough energy, it gets from the field, from the external field, and it ionizes the matter. And doing this, you can create avalanches of electrons and significantly improve your amplification. But it wasn't enough. The maximum gain that can be achieved with this type of detectors, you can see them. This is how it looks. It's just about 5 millimeters or 10 millimeters in diameter. It's pretty small device, and the main gain you can get is about 100, because you have one problem that applying high and high voltage, you are starting to get discharges, and you can produce this uniform structure. And this led to the problem that physicists starts to think about creating the actual device that can replace the photomultiplier tube, and came up with an idea which is called a silicon photomultiplier tube. And actually not use simply silicon photomultiplier. There are lots of names for this device, but originally I'm proud to say that this device was the idea. Silicon photomultiplier was belongs to Russian physicists, and they in 1980s constructed this device. What is their structure, and what is the advantage, and how they keep this thing that they can apply high voltages to this semiconductor structure? They decided to apply much higher voltage, much higher. And this voltage, like in gas field detector, it becomes Geiger mode regime, Geiger mode area. But as you remember from my previous lecture, that when you operate a detector in a Geiger mode, you lose all information about the energy. The number of created electrons is not proportional to the number of initial electrons. Here, number of initial electrons is proportional to the number of photons, and you lose this dependence. And in order to get rid of this problem, physicists created a matrix of small semiconductor structures, which are called pixels, like in our smartphones, where I have CCD detectors to detect light. They have a lot of pixels. The same thing with silicon photomultipliers. They have about modern detectors have about 20,000 these pixels, and these pixels, they are structured on the same substrate, and the reason they decided to create a lot of pixels because all pixel actually is an independent. And if you have, and they're pretty small, about 25, 35 micrometers. And when a photon hits a pixel, it creates, as in the conventional photodiodes, actually, this is an ensemble and a matrix of avalanche photodiodes. You have a lot of small photodiodes which are located and connected to each other. And when one photon strikes this pixel, you can measure the signal which it creates. If you have two photons, for example, the second one hits the near pixel and creates also the signal. And also you simply summarize all these pixels and get their signal, which is proportional to their original number of photons. Of course, there can be some problems if you have a very intense flashes of light. You may have a situation when, for example, two photons hit the same pixel. In this case, of course, you will lose the information about the initial energy, but this device was created specifically to detect low flash light, low flash supply, and it's used in many applications. It's not this device now hasn't fully replaced photomultiplier tubes because it's quite small. The maximum elements, you can see it here, it's about 6 by 6 millimeters. It's not big enough, and in order to create a significant area to detect light, we have to combine it and have a matrix of these silicon photomultipliers. And also, one advantage over photomultiplier tube is that in these silicon materials, you don't have to apply high electric field because the size is very small, several millimeters, and you apply up to 50 volts. If you compare to PNT, that's 1000 volts, and this allows you to get rid of high voltage systems, for example. Now, silicon photomultipliers found its application in scintillator detectors, of course, which are used in many applications, including fundamental physics, high energy physics. And apart from this fundamental applications, it's frequently used in such applications like LiDAR technologies, which are used for autonomous cars, for example. You have to detect light in order to measure distance between objects. In biophotonics, and in medical imaging, and this device is very important now. So, turn. Yeah, I think I got the turn forward. So, sometimes it's very important to connect. As you can see, you have a scintillator and you have a photodetector. You have to connect them properly in order to get to receive all the light which produced during the ionization process, excitation process, when the ionizing particle passing through this scintillation. And for connecting this photomultiplier tubes and scintillators, usually you use materials which are called light guides, which can transfer light by total internal reflection, which is similar to the process which is happens in optical cables for internet connection. You process light, and here you can collect as more photons as possible. That is why you use these light guides. And the second thing, if you have a solid scintillator, you have to cover it with some kind of reflector. If you don't cover it with a reflector, you lose a lot of light. It will go isotropical, in all directions, never lose it. But you want all that light to go to this photomultiplier tube. That is why you show, that is why you cover your scintillator with reflection materials, which can be, there are lots of ways to use different reflectors. Sometimes it's important to shift the wavelength of your light from, for example, a blue light to green light, and it's done by wavelength shifters. So I think I have covered all scintillator detectors and can move further because of time to talk about semiconductor materials which are used for detectors as well. And by covering these semiconductor materials, we can consider almost all conventional detectors which are used in gamma spectroscopy, in neutron detection, and so on, and move to more practical things, how to detect, for example, gamma rays, how measure their energy, and how to detect, for example, neutrons, and understand the energy of neutron, and then calculate the number of them. And here, just the last type of detector I would like to show you, which is called the solid-state detectors, which utilize semiconductor materials. Both semiconductor materials have this crystalline structure. Most semiconductor have zinc blende or diamond structure. A picture of a crystalline structure you can see here. We have a lattice, and in lattices, in dots of this lattice, there are atoms which form this beautiful structure. You have distance between them, which is usually measured in angstroms, and there are typical materials which are used for semiconductor detectors, germanium and silicon. In some applications now, we use diamond materials, but the main advantage of diamond is on the fact that it can withstand high radiation doses compared to germanium or silicon. And here again, this band structure, we have a valence band, conduction band, and a band gap between them. And the main difference, you can hear three types of materials: conductor, semiconductor, and insulation. And the main difference between all three types of materials, that's actually the width of this band gap. For insulators, you have this width more than 5 electron volts. And why insulators don't conduct electricity? That's because this value is pretty high, and the process of conductivity starts happening when you have electrons from this valence band that can overcome this barrier and go to the conduction band. If you look at the conductors, you can see that there is no this gap between conduction and valence bands, and electrons can freely go to this territory, and that's you have electric current, for example, in metals, which are good conductors. And in the semiconductor case, you have the gap, which is approximately equal to 1 electron volt, and in some cases, it can conduct current, and this property of semiconductors is used for radiation detectors. Electrons from this valence band can go to this conduction band in the case when you have pretty hot material, and the probability of electron go to this conduction band is described by this formula, and this formula just shows you that if you have more temperature, that probability is higher for electrons to go to this conduction band, and that is why in radiation detectors you have to keep this temperature as low as possible, because there are two processes which happen. Mostly in parallel, you have electrons that can go to this conduction band by means of thermal and the temperature, thermodynamic effects. And the second thing, they also can get some energy from the ionizing particle. And in this case, electron also can get some energy and go to this conduction band. But it happens that the majority of materials, germanium and silicon, it's extremely difficult to achieve the purity and properties that can allow you to operate the detectors in this matter. You always have a high level of these parasitic effects, high current, which is mostly from the thermodynamic emission. You have to come up with some idea how to reduce this thing. Here comes the so-called PM junction, which is used in diodes in many semiconductor modern devices. And just to remind you that in order to get this PM junction, you have to meet two materials, and these materials should contain P-type semiconductor, which is doped with elements like boron from the third column of the periodic element, and the second material should be from the fifth column in the periodic table, which is basically phosphor, for example, and you will get N-type semiconductor materials. If you meet them together, connect, of course, not just physically, but using specific techniques to increase the temperature and create this PM junction, that creates the region which is called space charge region, and this created by the fact that negative areas start to drift towards the area where there is a lack of them due to the diffusion process. The same for p-type materials. And you will get this space charge region, which is called a depletion region. And if you apply significant, actually this region is free of charge carriers. And if apply an electric field in the inverse direction, it will create actually a small semiconductor detector, and this area serves as a semiconductor detector. If we're coming back to semiconductor detectors, they start operating like typical ionization chambers. You apply two electrodes, one anode, one cathode, and apply an electric field between them. And instead of electrons and ions, you will have electrons and holes, which can drift also under the influence of electric field to the opposite electrode. And then you, by the same technique as for ionization chambers, you collect this electric charge. And this allows you to get an amplitude, and then again, you can convert it in the energy of the initial particle. But what is the reason why we start doing the same thing with semiconductors to create quite complicated structures and create this junction? And the main reason is that the energy which is required to create electron and hole is much less compared to the energy which is required to create electron ion pair. That's the property of these semiconductor materials, and the energy of this. If you remember from the last lecture, the energy which is required to create electron ion pair, for example, in argon, is about 30 electron volts. Here in these semiconductor detectors, we have the energy which create this electron hole pair, which is approximately equal to 3 band gap energy. The band gap energy is about 1 eV, and for silicon and germanium, the energy per electron hole pair is about 3. Here is the number. What it gives you, that you have more charge carriers in your detector. When you have charge carriers, you will have more strong signal, and this more strong signal allows you to get the perfect energy resolution in order to get excellent ability to distinguish between gamma rays sources and give separate gamma ray lines. But it will be the topic of my next lecture, about why we use different detectors for gamma spectrometry and why semiconductor detectors are the best devices to use for distinguishing between different gamma isotopes. Thanks for your attention. If you have questions, I can answer them. Okay, I can answer them tomorrow.
Muy bien. Como recomendación, por favor, mañana trataremos de pagar temprano, porque La penúltima sesión mañana, el día viernes, las clases van a ser de 1 hora, nada más, en realidad, porque vamos a poner el examen en la partida. Y continuar de la tarde, entonces, en este día, es un poco como desanimante para los cursos profesores, ver que no hay mucha gente que estamos empezando con 5, 6. Entonces, es muy agresivo por ejemplo, perdón, de estar más temprano mañana, ¿no? Entonces, esa era la recomendación que quería hacer. No sé si tienen alguna consulta. Ustedes. Ok, gracias por todo. Nos vemos mañana. Sí.
Sobre el examen inicial, ¿qué va a ser el formulario o va a ser escrito los que están presentes?
Estamos en este tipo de que sea online, si de preguntas como se hacen por el Google. La idea es que todas estén con sus ayudarás la presencia de la biblioteca. ¿Ya? Porque el examen solo va a ser permitido fuera, los que están inscritos fuera, el centro interior, en el exterior del país, fueron los que están inscritos para pasar clases presenciales y vigilar el examen presencial en la biblioteca. ¿Está? Listo, gracias. Entonces, vamos a ir a la-
Recording stopped.
Entonces nos vemos mañana a la misma hora para el examen.